Last week we started with fibers, and this week we're covering dispersion, everything we need to know for the basics. So uh, we started with what is dispersion. This the spreading of a um, optical signal in time domain. We'll see how it spreads also, like uh, using a MATLAB simulation. Also, we started with uh, this intermodal dispersion as a result of the different propagation velocity of each mode. Then we went and introduced the concept of bit rate distance product, how the trade-off happens. Then one important topic came up, phase velocity and group velocity. Uh, and using those expressions, we saw how material dispersion happens, which is basically chromatic dispersion, as uh, the different frequency components of the uh, optical signal are affected differently. And then we went and discussed waveguide dispersion and ended with polarization mode dispersion. So ultimately, this whole week we just covered path lengths and how long it takes to travel that path length by using this group velocity. So that was basically the encapsulation of the entire concept. And in the assignments and quizzes, we are asking this D parameter we used, dispersion coefficient that we specify as for single mode fiber, we use 17 picosecond per kilometer nanometer. So we're in saying what is the dispersion per kilometer of the length traveled, what is the length of the fiber that we are capturing in that coefficient, and also we are capturing the line width of the laser source. So that will also have an effect. So these are some of the results of the of some MATLAB simulations. So we are sending uh, an optical pulse, that is um, the laser has some line width, and we are directly modulating the laser because it's just a simulation. And due to dispersion, after just 1 kilometer, we can see the sharp edges have disappeared, and after like 10 kilometers, you will see uh, the blurring effect. Also, there are some spikes that corresponding to the sharp edges. And uh, I'll show you the code as well. At this point, after it gets this blurry, we'll start making mistakes when trying to decode this signal. So bit error rate will go very high. For this simulation, I think we get some 20% or so bit error. That is completely unacceptable. And at this point, we cannot uh, get any information out of it. Like it is very distorted. The dispersion is so bad that we cannot directly recover any signal. There are ways to, of course, uh, correct for it by using DSP techniques or inverting the dispersion effect. There are different methods, but without any processing, we cannot recover the data. Uh, this is a MATLAB code for this. So uh, there is some script. I'm repeating it for two different lengths of fiber. We are taking single mode fiber of 1 kilometer and 80 kilometer. We'll repeat. So we generate a signal, uh, then use a uh, laser with a given line width, This is a function we made. It basically uh, just captures how the phase noise is happening. Like we the random walk process we saw uh, during laser noise discussion, we're incorporating that. This will ultimately give a line width to our laser source, and so we modulate that using a Mach-Zehnder modulator. Uh, we could also do the direct modulation for the simulation of this specific thing, but what we need line width of the laser. Without different frequency components, you won't see chromatic dispersion. For chromatic dispersion, you will need different colors, right? Colors of the signal. That means the uh, frequency component of the signal. And the main working line of this whole process is this one. We are applying a basically we are applying a convolution integral, but instead of doing it in uh, time domain, it will come as a nonlinear Schrodinger equation. A differential equation will come. Instead of applying that, we are uh, taking an FFT of the signal to get the frequency components. We know the frequency domain transfer function, and this transfer function is then multiplied to the input signal. So we know the convolution in time domain is just multiplication in frequency domain. So doing this calculation in frequency domain is very easy. That's why we do it. Uh, there are some intricacies, but we can safely ignore some zero padding kind of issues. And this FFT, then IFFT shift, FFT shift up top, these are just uh, we want the continuous time Fourier transform, and but FFT gives result in a weird manner. Like it will start with zero frequency first, then the high negative frequencies will start later. So those kind of intricacies we are avoiding using these two lines. Uh, Taking FFT, then FFT shift. Like taking FFT of the input signal, then doing FFT shift. This is all the working code basically. And then we detect it using a photodiode. Photodiode has some noise also that we use, and then we plot those. These are just plotting, and we'll also see the magnitude spectrum. As we run the code, you'll see that the magnitude spectrum shows no difference because uh, the transformation that was applied, it will mess with the phases, but in frequency domain, it won't affect the magnitude. So you cannot say that this uh, magnitude spectrum was affected in any way, but you can see that the signals got blurred. This is for 80 kilometers, and we repeated it for 1 kilometer also. So at 1 kilometer, you will see the blurring is not that bad. You will see very little error also. Uh, how to decode this is a little more, slightly more involved. So we're not going there. But the 80 kilometer fiber, you can see without any dispersion compensation, you will get very bad bit error rate. Like this is 22% error. This is completely unacceptable. I think link design is coming at week 8. You will see we can tolerate one error in 10 to the power 9 bits. So this cannot happen in a link that we are using. So, but our span lengths are 80 kilometer, 40 kilometer, 80 kilometer, that kind of range. So we will have to transmit at this range, but we have to compensate for the dispersion. Dispersion compensating fiber we can use, or we can also use digital signal processing for this. So The whole transformation is just this transfer function is applied in frequency domain. That's it. That is the main working function. This whole code, what it does is just generates frames of data and sends frame by frame. Does all these um, whatever impairments happen, and then tries to decode it. That's it. So this is the MATLAB uh, code that you can use to check dispersion in fiber. Uh, I think that's it from my side.
So thank you, Janek.
Okay, I'll share the codes. I have to edit a little bit because like these were codes written for some other purpose. So I'll add comments and stuff. We'll share in the forum. Okay.
Sir, can I know how the dispersion compensating fibers are made?
I forgot. Okay, I'll check and tell you. Okay.
Okay,
What's
sir.
what's question, Namita?
So, how the dispersion compensating fibers are made?
Okay, how I'm manufacturing that?
Yes, sir. So, actually, as I know the formula, alpha attenuation into length of a single mode fiber must be equal to the attenuation of dispersion compensating fiber into length of dispersion compensating fiber in order to compensate the dispersion in a whole optical communication link.
Yeah,
So,
but the basic problem is that we need negative dispersion coefficient,
Yes,
right?
sir.
That's
Yes,
the
sir.
thing.
So
Okay.
that's why I'm asking how these are manufactured.
Okay, I'll check and tell. Like I don't remember exactly.
are you talking about single mode or multi mode for that, Namita?
So yes, sir.
Single mode or multi mode? Because as per the what type of dispersion you want to minimize that.
So I think generally we are using single mode fiber only.
Yeah,
Um,
single mode, single.
Yeah, single
so
mode
I
is.
have many questions. First of all, I just want to know, like for the fiber to the home. So we are using single mode fiber or multi mode fiber.
Fiber to whom we have used the single mode.
Multimode is very rare.
Multi modes, because there is mode type of the dispersion in the single mode only one type. It is only material dispersion. But in the single mode we have the chromatic dispersion like the waveguide dispersion or the intramodal or intermodal dispersion. So we cannot minimize that in that case multi mode.
So
There
we are
is
using multi mode fiber,
no single mode fiber in that case
single mode
for
fiber, no?
most probably we use the single mode fiber for that.
Ashok sir, please can you share your email address with me? I have one doubt in one numerical question. I will share that numerical question with you so that I can
You can
understand the
share, you
answer of
can
that.
on previous assignment or on this assignment.
Okay, sir.
No, which assignment you talking about it?
So no, I'm not talking about any assignment. I'm just practicing one question from Ghatak. So I'm having one
You can
problem in
post,
that.
you can post on that Google Classroom. You have access that, na?
Okay, sir. Okay, sir. Okay, sir.
Or you can post to ask to form also that. I will look and Jonek will also look onto that also both.
Okay, sir. Okay,
Okay.
sir.
So you have the
Okay,
both
sir.
the options. From my side, I have access of the Google Classroom, and for if you share on to NPTEL team, then you can to ask to form that discussion form also. You can put your questions that
Okay, sir.
regarding
Okay, sir.
MATLAB or whatever that you have doubt till that lectures that.
Okay, sir.
Okay. So
Yes, sir.
I have remind that also that every time that you have to put that question, so we will take on that every session, but no one have put on that Google Classroom or anything that. So any other regarding MATLAB, any other doubt regarding dispersion that MATLAB how to code and that. Apart from Namita, there are 13 or 12 students. Are you there? Akansa? Nilima? Achal? Manish? Manish, are you there?
I'm here.
So have you any doubt regarding that? Previously, you can ask that.
Yeah, I have to ask question 3 in assignment. This assignment 6.
Okay. For 6 assignment questions, 3.
Yep.
Okay, we will take that also. That accumulated dispersion.
Correct. Correct. Accumulated dispersion in the fiber if the length is 100 kilometer while operating at the 1540 nanometer.
Okay, okay. Okay. Okay, we will take that questions. I will take that.
Okay. Thank you.
Any other one are present or only Namita and Manish is there?
Praveen sir,
Who is this?
Samuel, Samuel sir.
So have you any doubt? Anything that regarding this course with assignment from 1 to 6 or any facing that difficulty to understanding that subject or everything is
Problem,
fine?
some problems are related to this question.
What?
Table column regarding the table column, not the first question. So according to table, first question, like that.
For
Any
assignment 6.
yes sir,
So you have doubt on the first question.
yes sir, yes sir. Just explanation.
Okay, okay.
Thank you.
So other anyone other? Lavanya, Devsri, Minakshi, no one is there. So, what you mean by the dispersion? Can anyone tell me that?
So dispersion is basically a broadening of light pulse as it travels down the length of fiber, and dispersion causes distortion for analog to digital signals, and it causes intersymbol interferences.
Okay. So, what is the reason? What type? Why we happen in a dispersion in that optical fiber?
So because if I talk about so in a multimode fiber, like if a light rays, if like we have axial rays and we have meridional ray concept. So like axial ray is coming at different time with different velocity, and another ray is moving with different time and at different velocity. Due to that, we have the pulse broadening.
Okay, pulse broadening is that. Another reason anyone can tell apart from Namita that Manish and that Anchal. Anyone can unmute yourself and can answer that.
Sir, in optical fiber, ray is transmitted or mode is transmitted?
Mode mode will be, but it will be in the form of light only. There is how much mode will be transmitted, we can calculate by v square by 2 na.
So
Sir, mode is related to ray.
We
uh,
form.
the ray picture is not accurate, but it's accurate enough for a lot of things. That's why we use the ray picture. Ultimately, we will be solving Maxwell's equation and
Yes.
modes we introduced last week. But you don't need to get the full vectorial Maxwell's equation kind of complexity. If the ray picture does the job, why go for more complexity?
So, in which kind of fibers Q ray is propagating? Like we have two rays, meridianal rays and skew rays. So, in skew ray is also propagating in a multi-mode or single-mode fiber, or it is a special kind of fiber in which skew ray is propagating.
For single mode fiber, I don't think uh, you'll get like different modes like that one mode and it's like LP01X and LP01Y is degenerate polarization mode. Those are the only modes that are supported in a single mode fiber. But if you make the fiber diameter higher, it will still guide light and it will also support uh, more modes. So I think for skew rays you will need larger core diameter. Single
Skew rays
mode
is
fiber, I
propagating
don't.
in multi-mode graded index or multi-mode step index.
That I'm not sure about. I don't want to give you a wrong answer. So again, let me check and get back there.
So what type of dispersion occur in single mode fiber and multi mode fiber? Can you distinguish between that, differentiate?
So in multi-mode fiber, we have intermodal dispersion.
Okay.
Material dispersion.
Yes. Other than that.
Waveguide dispersion.
Okay.
Propagation dispersion is waveguide dispersion. Sorry.
What is Manish?
Propagation dispersion, because different in case of multimode fiber, different kind of lights are propagating in a different time traveling. So by virtue of which there are a lot of dispersion.
It is I think classification of intramodal dispersion. I think so.
Yes, yes. So what is the difference between intermodal and intramodal?
So it is intramodal. It is because of the optical light sources. As the optical light source does not emit a single frequency but a spectrum of frequencies.
Mm.
So it is due to the spectral width of the optical source.
Okay.
And intermodal is due to the different group velocity of different waves.
Okay. And what is the material dispersion? Single mode fiber have material dispersion or intermodal or intermodal?
So material dispersion, no intermodal dispersion.
Okay. So we can minimize the material dispersion or not in fiber? It is possible
So can
practically.
you please pardon?
Can we minimize the material dispersion in optical fiber or not? It practically.
So we cannot.
And how can we minimize that intramodal and intermodal dispersion? It is
So
possible.
if we use highly coherent, if we are replacing LED with the laser source, then it will be minimized.
Okay, that case we can minimize intermodal. So then intermodal, if the two signal will be travel and it will be interface, then how can we minimize that time or pulse width and that duration of that? Like that, one pulse is traveling like this. It have delta t travel time. It have a spectrum like that is bandwidth spectrum of delta t. Another pulse is travel like that, and it have delta t. Okay, so in that case it has some extra.
Yes, sir.
So how can we minimize that in that case? Apart from that, Namita and Manish, please, there are 14 students. I need your participation also. That Achal, Ria, I think. Parmul Vidya, are you there? Ramya, Sandeep, Sanjeev. So dispersion in optical fiber usually contained through the spread in the time domain. So whatever wavelength the laser will be travel that light, it will be spread in that in the time domain form in that delta t. Whatever that t time, it will spread at t plus delta t in that case. Some spreading will be happening in the optical fiber. So it propagate through the fiber, that will be spreading that through the some region is there. So the region is the material dispersion, the presence of the different frequency in the input pulse, that is a material. So material like that, some fiber will be made SiO2, some made of the glass, some made of that PMMA type fiber. So due to that, whatever the source of light we that travel through that optical fiber, it make the dispersion or it may be spreading that laser light, that time period at t. In that case, in intermodal dispersion, different mode propagate through the different ray path, like that. Some mode is like the travel this path, some mode will be travel like this path, some like that this path. So it will be may interface in that case. Waveguide or intermodal dispersion is the same, different velocity, that already told by that Namita is right, that because their evidence and effective last in the week 5 class you see that n effective equal to lambda by 2, some that formula through that. So its refractive index will be changed, that velocity will be changed, because phase velocity normally we see like c by n. Okay, so if n is the refractive index here, c at the velocity of that light, and that n the refractive index will be changed, that maybe that velocity will be changed, and it like that one wave will travel like that faster, another wave is in the slow like that. So it may be create that some period of time it may be interface with each other, and it create a dispersion, and it will be lost of the information in that optical fiber. So in the single mode fiber we have only the material dispersion, because only one wavelength of light will be travel through that. But in the multi-mode fiber we have all the three dispersion. So in practically we cannot use the multi-mode fiber. But if the index profile will be, if the graded type index profile, then some sort of distance we can use that multi-mode fiber. But for long distance we use only that single mode fiber, that in that case. So, what is the impact of the intermodal dispersion in optical fiber, and how to improve the bit rate product? Can you tell me, anyone? Now, who joined recently? Jagannath Naik. Jagannath.
Yes, sir. Sir, there is a network issue. I am trying to join, but
So now it is okay. I think that your voice is also audible. And can you tell me that what is the impact of the intermodal dispersion, or what is the dispersion you mean by that dispersion? Jagannath.
hello.
Can you briefly about that dispersion? Yes, yes, your voice is
What, sir?
audible. What is the dispersion, and how can we minimize the intermodal dispersion? That waveguide dispersion and that.
Dispersion.
What is the dispersion you mean by the dispersion? Just basic definition you can tell me. Not I need just your understanding for that.
So dispersion is defined as the separation of light into colors by refraction and diffraction from spectrum.
What what is?
The splitting of white light into different colors with a spectrum is called as diffraction.
So splitting of the light.
Yes, sir.
It is splitting in the term of the frequency or time domain where it will be splitting, or in term of the
Yes,
amplitude.
it is in the term of frequency and intensity, sir.
Intensity splitting means it will be create a dispersion.
Sir?
Intensity, if the amplitude will be change of that light, it will create a dispersion. It is good questions.
Yes,
Namita, it is correct. Manish, Manish, can amplitude will be responsible for the dispersion?
no.
Why?
So it's basically width means sir, it depends on frequency and wavelength.
Jagannath, please listen to Manish and then you can speak.
See, basically amplitude is nothing to do with the dispersion. Is basically the width of a frequency. Basically, suppose omega naught is the central frequency, and at a different time of interval of the rays. So amplitude is not going to impact the dispersion. It's basically the phase which is going to impact the dispersion.
Okay. So Jagannath, that is
Will
understood.
get reduced.
But it will not. We will signal will be that intensity will be reduced, but it will not.
Absolutely,
It will be not
absolutely,
make the interference of the symbol.
exactly. Correct.
Okay. Yeah, intensity will after traveling some time or some length, it will be maybe we get the less intensity at the output side, but it will not the loss of the signal. It maybe create some noise due to noise also that interference will be happen in that signal. That intensity may be increase or decrease in that case also. Signal to noise ratio will be depend on that case. How much your signal to noise ratio of that. But Jonek,
Yeah.
can you clarify that amplitude will be happen that not?
No, no.
Yes. So Jagannath, have you understand that? Hello. Are you getting
No.
point?
Yes, sir.
So that's
So
why that's why this class is important. Now you have asked a doubt. You have to clear about that amplitude, phase, and that spreading of light. If you not speak, everyone will be that loss. It is your loss, not me and that Jonek.
sir, just
Yes.
tell me one thing, sir. As we
Okay, sir.
transmitted 1011.
Okay.
So can you please note it down with me so that
One
it will
zero
be
one
clear
one.
to everyone? So
Okay.
how this is transmitted through optical fiber?
It's depend upon that coding that if you use that non return to zero
So
on off
if I'm using return to zero, then how will it will be it will be propagated through the fiber?
like that, this signal will be returned to zero.
Yes, sir. Yes, sir.
Okay. So we
Yes,
have
sir.
to this one, this is zero, this is one, and then again one we have to again one that continue that.
Yes, sir. Yes, sir.
Okay. So this
Yes,
will be
sir.
So
the
this is
waveform.
non-return to zero, and in return to zero, you will be. Hmm,
What
uh,
Jonek?
this is non-return to zero.
Yes. No, no,
Yeah.
this is return to zero.
This
It will
return
become
to
zero.
zero, sir.
Non-return to zero will be Jonek like that.
Yes, sir. Yes, sir. You are right.
Because that zero will be we have put 0 volt on zero. It will return to zero again. That one we have to put that 5 volt or 2 volt that.
No, no. I'm pretty sure. Like, ma'am taught me this. The top picture is non-return to zero.
This will
Return
be
to zero will return to zero at each symbol. Like for transmitting one for the half of the symbol period, it will transmit 1 and then return to 0.
So this is
So
the
it's not
second one.
centered at 0.
Second one is return to zero, and this first one is not return to zero. Are you like that telling?
No, no, second one is not used in optical communication.
Yes, in optical, in not we can use that. We
Yeah.
use that like on off key switching like that on that modulation. We can base some that in that Mach
So
Zehnder.
communications people will see that
Yes,
return to 0 thing. It's just
communication. They
BPSK.
yes, yes,
Yeah.
communication is they were using that like that. So, Namita,
Yes, sir.
any other questions on that?
So how this is propagating within the fiber?
So
Like
it
how
will be
this is
convert it will be convert into bit, and then we have to transfer that in the converted to then optical laser light source then.
so
It's
how like
basically
how
This
this
is
switching
the
on
link.
and off.
switching
It
on
is,
and yes, John, continue.
So can you please make me understand how this is propagating in a fiber?
Like that laser light that no, that is signal will become like that, like light will be go like that, and that propagate through that laser that light through the laser light. So it
Okay,
will
sir.
that in a total interrelation we see like that either in this form light will be travel. So we have include this it's that signal either you form the sinusoidal signal cosine that so you have to need which form you need that rectangle pulse or a square pulse. So you make that optical converter on that, and you can convert that to that laser light into that form, and you can send through that optical fiber. So you can send it a sine form, cosine form, triangular, rectangle, whatever that you can want to form that you can send it through that fiber. Jonek, right that?
yeah. So laser will generate some whatever terahertz, 1550 nanometer. Uh,
193.1
yeah, yeah.
terahertz.
Yes.
So uh, we will encode the information in just the envelope. For a simpler picture, just imagine turning that laser pointer on and off. That's it.
Okay, sir. Okay, sir. Okay, sir.
So that impact of the internal dispersion on data rate in the optical fiber communication. So it will make the mismatch in the data rate. That bandwidth may be mismatch in that case, or inter single interference will be happen in that intermodal dispersion. So what is the bit rate product in that case? Anyone can tell bitrate product about that, like that bitrate we have communication before. You have also read about bitrate, baud rate,
So
plus
it must be less than equal to 1 by 2 tau.
not that like that sampling frequency in this there is yeah it's like that only, but related to like that sampling frequency like that only. One minute, I will explain that. Like that, this is the our bandwidth product. This is one slot of bandwidth. Okay, one signal slot time t. Okay, so we have mentioned is the TB. So the signal transmission bit rate we have to assign with the bit, like that. This is the signal, my sinusoidal signal. Okay, and this is the interval through total interval of like that. If the sinusoidal signal is like that, so this is my TB whole, and this is my TB by 2. Okay, so when the this pulse will be propagated through the optical fiber, this is the fiber like that. This is the just for that for your convenience. So what is happen that whatever the time period of this pulse is the TB, so it will be spread like that. It will be spreading like that. It is TB and it will delta TB. So it will some time will be split in that case. It will TB by 2 is also spreading in that case. Some portion will be, it will take more interval. Mean TB plus delta T. Some interval will be spread in that case. or maybe it will be take less, not depend, it will be take more, it will be take less duration of time also, or it will be more, both the way it possible in that case. So what happen, it will create the inter-symbol interference, because one light have like that this TB, and one light have like that this only, this duration, this duration. Now it, if the dispersion will take in this palace and it take this time only, same time of that second wave, so it will be interface both the signal in that case. So our delta T should be less than equal to TB. So this time may be, the interface may be less than TB or more TB. So okay, so whatever happen, that if you take this product of delta TB TD, it should be less than equal to 1 always. Okay, so beta n1 is the refractive index of port and cladding, n2 square into length of fiber and speed of that laser into duration of that time, that the delta should be less than equal to 1, this formula. So we have calculate, this is the bit rate product, beta L should be that bit rate product here, so it will less than equal to n2c, so this is not square error, okay, and this is n1 square into delta. So our bit length, bit rate product should be less than equal to n2 is the refractive index of the cladding, and c is the speed of the light, into n1 square is the core, and delta should be that n2 minus n1 but n2, that n1 delta should be that. Okay, so this is our bit rate product. So for example, I will erase that. So I have taken one example for you. So how the bit rate will be affect that communication in that case, whatever change. So we have the optical fiber. So n1 equal to 1.5 and n2 equal to 1. So bit rate product we have calculate like that 0.4 Mbps kilometer. So if there is a requirement of transporting of the 1 Mbps over 100 meter, we have the requirement of the 1 Mbps that bit that speed of that signal, that 1 Mbps per second with that speed over length of 100 meter. Then the fiber is sufficient, since the largest supported bit rate of length 100 meter, because we require bit length product of 0.4 Mbps, but our fiber support that 1 Mbps. So it will be transmit that, easily transmit that product on 100 meter. However, if there is a requirement of transporting 1 upon 1 kilometer, then the above described fiber is the efficient. You can understand that how this is significance of the bit rate. Student, this example, can you briefly that what is the significance of the bit length, bit product, bit rate product? Namita, Manish, anyone can tell me that. From this example, how can you understand that what is the significance of bit rate product in the optical fiber? Hello? So another question for you, to get a feel for magnitude spread, we consider following example. Okay, na? We have the view date of the 25 gigabit, is time duration of the bit slot at TB is equal to 0.4 nanosecond. So let the pulse width of the Gaussian input pulse that this is the Gaussian input pulse. This speed is up to tau. Okay, this pulse. This is 20 picosecond. Carrier wavelength, this wavelength of that laser is 15 to 15 nanometers, and carrier frequency, that this frequency fc. So wc w naught we defined at 2 pi f, and you have to given the fc. Okay, so you can calculate that w naught. So we have to that whatever the speed, that delta w in that speed in that case this laser upon that actual width of that pulse is w naught, and that spreading happened at delta w. So we calculate this through that vp, that frequency, that group frequency and phase frequency, that through that phase frequency equal to 40 by omega naught. T naught you have to given that 20 picosecond, and w naught you have to given. So it will come around that 3 into 10 to the power minus 4. So when you transmitting that 25 gigabit, that signal, that view, that is about 25 gigabit, the frequency is compared to the carrier frequency fc. So what is the fc? From that you can calculate that through the fc, that 2 pi c dot lambda. Okay, so this will become 2 pi cf 2 pi f omega naught equal to, from uh, so omega naught, from you can calculate the fc. So maybe it will become around 3, but it change due to the spreading is order of 10 to the power minus 4. Due to the spreading or dispersion, is order will be changed into 10 to the power minus 4. So, so this is the relative speed around the center frequency, or which the variation of the refractive index the matter. Okay, so what happened is change due to refractive index means it to the material dispersion. That's why some change in the carrier frequency, center frequency will shift from both the sides of the 10 to the power minus 4 order from the center frequency. So it is fc, and some wave may be shift from this side, and some signal wave may be this side from the center frequency due to the refracting index that fiber. So this is the example of the material dispersion happen in this optical fiber. So you can see that it will shifting around that order of the 10 to the power minus 4.
Sir, I have one more doubt. Can I ask right now?
Yes, yes, yes.
Sir, like if we have the critical angle of 80.4 degree,
What?
so
Theta c.
80.4 degree critical angle, yes sir, yes sir. So can you please able to tell me what is the range of the incidence angle so that the light will achieve TIR?
Last time I have said the condition that theta c pi by 2, like that the condition is less than 0, that between that one
Okay, sir.
that I have shown
Sir,
that
actually, I got that by that I got the transmitted by this pi by 2 minus theta c.
that delta
I got
t
9 degree.
delta
Yes,
t.
sir.
So you have the relation between that, like that
Sir,
one.
I got the value of 9 degree.
Okay.
But the sir answer is showing the range from in the answers we have option 0 to 80. Like from the incidence angle, like critical angle is 80
We
80.
yes, yes.
So
So
so in
we
option we have 81 to 90.
okay.
So I just mark that option 81 to 90 degrees Celsius. 81 to 90 degrees.
We have that in that type numerical question, we that like that in the get we have given that range, that because someone take like that in the parameter, in that case some constant will be take depend. So we have take the value of the range, it's no problem that,
Okay, sir.
like that this is our theta I, and this is our theta I, and there is your theta t, and this is theta c your. Okay, so you can calculate from this angle both, because this mathematics equation, that theta c value. So that's why there's theta c should be pi by 2, that theta t some value this. Last time I have in my video also I have put that equation, that condition, that in that case.
Yes, sir. Sir, I got value of 9 degree. I think, sir, I'll ask you in what's in mail.
Okay.
I'll send you that question in Gmail so that you will be able to understand more about my
Okay.
question.
Okay. 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 So what is the phase velocity and group velocity? Anyone can answer that?
See, waves can be travel in a group.
Okay.
So, so wave which are known as a wave packets. So velocity with which the wave packets are travel are known as a group velocity. And phase is the basically the velocity with which the phase is traveling. Basically, with the change of phase, the velocity is going to be travel is known as a phase velocity.
Okay.
So that's why it should be a d omega dB by d omega inverse because it's because of the phase.
Okay.
We have heard in the
Yes,
map.
yes, yeah. This is the phase. Beta should be. Okay, we have to include
Correct.
that phase.
Yes.
Okay, and d omega that with the frequency change with that. But in the case of that phase velocity, beta should be we keep the phase in that constant in that case. So group velocity in the finite time the more relative parameter Vg that in a pulse with the finite speed. So this is the speed due to the pulse omega that. Okay. So Vg is just omega beta beta and this is equivalent to C by N is your refracting index only that. In that case we have keep this is the constant so we maybe alternate we can talk that C by N that. So this is that so this is the normal in rays that travel through the fiber standard that in practice theoretically that we expect that
N here is equal to beta.
yeah
N is the refractive index here.
yeah N is the refractive index.
Yes, sir. Sir, it is for a monochromatic only or any other?
This is for monochromatic wave only. Phase
Yes.
velocity we can for monochromatic we can count that because we take the only phase of the one laser wavelength of light only. Every laser light have the different phase velocity. That maybe in the single mode fiber we have only propagate one wavelength of fiber, but in multi-port we can multi wavelength can be travel through the fiber. So every have that different velocity of that travel. That's why that dispersion will be happen due to because they have the different velocity or phase velocity in that case. So we have to calculate that every laser lights wavelength in that case, phase velocity in that case. But we keep that n will be that constant in that case that or phase will be that change in that case that how much the phase will be travel that angle will be take that. So this is that for standard that we take 1 by c and for that like that standard like that travel that linear region will be take like that this will be travel like that only. But anyhow due to that dispersion some that maybe some that this change in that happen in that case but standard will be like dot will become that that's why we have divided it by n that case. And in this case of the group velocity we have change here that is spreading will be happen in this area that with the normal it will be happen some spreading in that case. So this is w and change in that spreading of wavelength which we can take that delta w in that case. So this is the assignment questions. So I think that Manish have some doubt in that questions 3. So Manish, I think I will explain here only. So Manish, in that questions, you have given the length of the fiber of 80 kilometer, and of lambda equal to you given that 15, 40 nanometer, and you need to find the accumulated dispersion. So accumulated dispersion, I mentioned AD equal to delta T upon delta lambda. Okay, so
Okay.
delta T you can calculate that from data table. That I have already given that delta T should be less equal to that formula that you given that N2C, some formula is there in that madam have asked you some formula. From
Yeah.
that you equation that value delta T and delta lambda. So change in the wavelength you are also given that in the that table, that first question. That so delta lambda in that case, I think they should take the value like that, around 1 nanometer change in the wavelength from that evocations. And so it will become around, so you have to given that L, so delta D you see that DL, you take the length of that fiber, and delta change from that you that refractive index you given that, so you delta you can calculate that n2 minus n1 by n1, and L you have to given, and uh, D you have to calculate that accumulated dispersion, and delta T from that above equation you can calculate, and the delta lambda is, I have already mentioned, 1 nanometer. So from these things you can calculate that value. Okay, Manish.
Fine. I'll do it.
And one more questions, who will ask me? Who will ask me that, find that, are you there? So one more questions, someone have asked me that. Okay, so I will take the assignment questions. So consider that that beta length product from that Manish, that delta T by lambda I have given that value, this formula.
Okay, okay, okay.
Okay,
Yep. Thank you.
so you can take that help, and that also. If you have any doubt in that, you can post that also, I will help you that.
Sure.
Okay, I will be, every time I will check every day that classroom and that discussion form that, so you can post that anytime, that we take every day that. So consider a 1 kilometer long multiple extended fiber which have a different index of n1 equal to 1.4 delta, that change in that refractive index. What is the more delay per length in this fiber? So delta T is the delay, and that L is the per length of the fiber. Also maximum bit rate that can be expressed through the fiber. How much the bit rate, that bit rate product we can calculate. So delta you can calculate from this formula. So N2 you have to missing in that case. So here is the formula, n1 square delta upon C n2. In place of the n2 you can push this formula, and you can calculate delta T beta L. And this formula, so you have to bit rate product, I have already explained before that, in that case bit rate product. So C n2 into n1 square delta, you put the C n2 value, n1 square, that you put this value, n2 in place of the n2 you put this value, and you can calculate bit length product of that also. So what is the largest length of the transmission possible in the 10 gigabyte under PMDSC? Propagation modulation dispersion of 0.2 second under if a maximum of 10% speed permissible due to the PMD. So delta T or delta X is given our given 10%, we can disperse that fiber that. So this is the frequency, and this is the dispersion group delay. Okay, this is a dispersion group delay, and this is the propagation that constant that we have taken in the Gaussian form. This is the signal, so we have taken one Gaussian under the curve of the signal under the Gaussian curve. Through this we have to given that PMDC you have to given 0.0 picosecond, and PMDC is directly proportional to root of length of the fiber, square root of length of the fiber. So delta T you given to the 10%, that we calculate 0.01 nanosecond in that case. So from that delta T, and from that PMDC we have the formula that root length square can be 0.01 but a 0. PMDC, that propagation mode delay dispersion. Okay, that we can calculate. So this will around come 25 into 10 for 10 kilometer per second. So these questions will be not maybe in your assignment, and so I have taken from that classroom or somewhere else. So a propagation, during that propagation of the light some dispersion will be take place in that constant. So that's why we take the Gaussian curve in that case to that whole the signal we converted in the form of the Gaussian form, and we have taken that under the curve under the area that of that how much the signal that pass through that output side of that in that case. So anyone have any questions? So Jonak, can we stop?
For this, okay, let's show you one or two YouTube videos. The concept of this group velocity and phase velocity, you can see by seeing this finite difference time domain solvers that solve this Maxwell's equations uh, by converting the differential equations to difference equations. Is the audio working? So uh, you can see this how the envelope is traveling at a slower speed, slower velocity, and the phase is changing faster. Like you can see that we can posting the link in the chat also if you want to see
Yes,
this.
you share. I will stop that. They maybe have more understand that.
So the phase is changing faster, but the group is moving slightly slower. Uh, so the group velocity is slower, you can see clearly, but the phase is changing quicker. So the concept of phase velocity and group velocity, you can see by slowing this uh, propagation down to human scales. That's all I wanted to share with you.
So this circle is the phase or that above on that, Jonak?
Circle is a waveguide structure.
Okay.
So this is probably a silicon photonics. Uh,
Okay, this is a ring,
these,
the ring type similar that ring module, that ring modulator.
yeah.
Yes.
So we're showing cross section of a uh, probably 400 nanometer height of silicon in
Okay.
embedded in silica.
Okay. Okay.
So these waveguides are of refractive index 3.4 or something, and silica is 1.5. We know,
Yes. Yes.
and we're sending a pulse.
Yes.
This it gets coupled into the ring.
Yes. Yes.
This is a ring resonator
Ye-
popular in silicon photonics applications.
Yes. Yes.
The objective was just to show how the
Yes. You can
phase fronts
feel.
are moving and how the group
Yes,
is
you can
moving.
feel
That's
that how much how light will be travel through the fiber and the group and phase velocity will be changed that case.
this is exactly a simulation of light.
Yes.
So obviously it's slowed down to human scale, but
Yes. Yes.
okay, that's all.
So please post your questions on that Google Classroom or Ask to form. So we take in the next time that next session next Tuesday. Anyone have any doubt or should we stop that? Okay, thank you. We will meet on next Tuesday again.
Thank you, sir.
Jagannath, I'm posting on the forum. Okay.
Yes,
See
sorry,
you.
you're not audible. Please once more.
Uh, the detailed thing I'm posting in the forum in NPTEL. Ask a question. There is an option on top of the course page.
Yes, sir.
Your question I'm answering there.
Yes, sir. Yes, sir. So how do I get my solution?
You can log in that Swam portal, and that there is a, that one tab that asks two questions, that there you can get that, or you have get
Okay.
also email that also, that maybe.
Okay, sir.
So you have to log in that portal, and there is also uploaded of the transcript of this class, and video is there, so you can go through that video, and some formula of the transcript we have written, that Jonek will written every video converted into the transcript form, so you can read that also, that is accessed by that Jonek there, this student.
It's in the NPTEL portal. Up to week 9, the transcripts
Yes.
of each video should be available.
Yeah, so you can go through that transcript also. Some there is a formula and some basic explanation of the all the things is there.
Yes,
Okay,
sir.
thank you. Okay, thank you, Jonek.
Okay.
Jonek,
Yeah.
tomorrow I will be traveling, so maybe in the not able to join meeting. I'm
Just mail, ma'am. Just
yeah, I will drop one mail that now also that.
okay. Okay.
Okay, okay.
Happy journey.
Yeah, okay.